Sweet. So as you all know, as you probably have recognized by now, we're finally coming to the end of this course and the semester. Today, we're going to give a 2-hour lecture on machine learning, decision trees and random forests, and so on. And tomorrow, Metha, I believe, is coming in for a lecture, a perspective seminar, which should be great. The last two have been great, so I'm really looking forward to this one. And yeah, maybe a few of us will be here in person, a few of us in the lecture team. So potentially you'll see us here. The content we cover today is going to be relevant to also project 3, as well as all the work we've done on data frames and so on. So project 2 has just been handed in last Friday, as I understand it. Project 3 is due towards the end, or basically at the end of your examination period. If you remember the interesting marking scheme for this course, essentially, you can essentially think that your best 2 marks on the 3 projects are the ones that count, and we'll discard your worst mark. Yeah. Now you don't even know your marks for project 2, so yet. So you know, you don't want to game the system and just think 2 projects is enough. There's a lot of interesting stuff in project 3, which is sort of relevant, could be relevant for your future careers and things potentially as well. So sort of probably the most interesting stuff is that last one. So yeah, and I believe on Thursday there's a practical, it's my understanding, for project 3. So project 3, I don't really want to go into it, but it's the same thing as previously with the perspective seminar questions and then the main project. It's going to be exploratory data analysis and then making a machine learning model with a random forest out of this data set. So it's an interesting data set about house prices in Melbourne, and you'll be able to do things like predict the price of a house given how many bedrooms it is and how many kilometers from the city it is and so on, which is actually a real life thing that people do, because you know, like if a real estate agent can price a house more accurately, that means they can probably get more money selling it, so they don't underprice it, and vice versa. It's useful for purchasers to know what things will go for. I was going to say yesterday, but Tuesday. Tuesday, let's go down to the bottom of this. Tuesday, we started dealing with machine learning and machine learning data sets. So remember there's this famous data set called MNIST. This will come up again today. And you could kind of see that from you know, just consider anything an image or any other kind of data as just a vector of each one of these could be flattened into a vector. And it's from these vectors that we want to make predictions, okay? So you can look at the vectors in some subspace, you know, and you can use, here's an example of using machine learning to go from that vector to a string, in this case, what type of apple it might be. And, you know, we had a little bit of a look at linear models and gradient descent. So these graphs here at the end have to do with, we had to skip this last time, basically. Sometimes your machine learning models are so large, your training set might have billions of rows or millions of rows, or they might be lots and lots of features. That it's expensive to train with the whole data set. So what you do is you train a little bit with a little bit of the data, then you train a little bit with a little bit more of the data, and you take little steps downhill towards you know, the best loss function or cost function, or you know, it's basically, as I mentioned on Tuesday, it's basically an optimization problem, trying to figure out what's the best machine learning model to fit this data. And so you can end up with trajectories like this, where you might start down here and it'll go bounce around and bounce around and bounce around. And you can see this is an example of a stiff problem, where it's very quickly getting onto this line, but very slowly moving in this, along this line. And yeah. So if you are following along on the lecture slides on your computer, please click the little button which says to be continued here, and it will open up unit 7b. We just did this because, you know, the page is getting a bit long. And it takes us a long time to actually render the page and so on. So today we'll talk a little bit about fitting and overfitting, and we'll move on to decision trees and implementation of a decision tree, how random forests work, and so on. And we'll see how much time we have at the end for further discussion. But yeah. Are there any comments or questions before we get into the material proper? Stiff. Yeah, no, that's a great question. So a stiff, sometimes it's really easy to find an optimal point. Like if you imagine like a bowl and you put a ball in the bowl and it rolls downhill and it goes to the bottom, it'll kind of get there pretty easily, right? You can find your way. Now imagine instead of a circular bowl, you had like a really, really, really narrow, long, thin chasm, okay? So like a canyon, right? And you have this canyon with this little bumpy river at the bottom of the canyon, and your job is to find the bottom bump of the entire canyon. It's a bit harder because you're kind of constrained and you're kind of trying to explore this two-dimensional surface. But if you get a little bit, if you go a little bit to the right, you're suddenly on top of the cliff, right? And the computer can easily get a bit tripped up and confused because it doesn't really understand cliffs when you're using derivatives. It expects everything to be smooth and easy and so on. So one of the hallmarks of a stiff problem is some of the dimensions are really easy to solve and some of the other sort of orthogonal dimensions to those. You know, if you can imagine a canyon as, like you can imagine a bowl as a small circular parabolic shape or an elliptical sort of shape. As you make it more and more squashed, you know, the contours in that cost surface become like ellipses, right? And so as that becomes more drawn out and elliptical, it becomes harder to solve. Now, this becomes more of a problem when that ellipticity, it's not like 1 or 2 or 3, it's like 10 to the 5 or 10 to the 10, you know, it can be a very, very large, different in ratios. And that can even be a problem with numerics, because if the stiffness is 10 to the 10 and you're using single precision floats, you might not even have enough precision to make sure you don't, you know, end up on top of the cliff on every step. You know, you get stuck. So yeah, but that's a real practical problem that happens a lot in reality, is that a lot of interesting problems there. Okay. Okay, fitting, overfitting, generalization, and model choice. Okay, so we'll just talk about some generic stuff about machine learning models. So the idea with supervised learning that we're going to do is you're going to find some model. So a model is some guess at the solution, okay? So for example, you might see some points on a graph and you want to fit a straight line. The straight line is the model, right? And once you train the model, it's like when you have the slope and the intercept of the line, and you can have an exact model. So the class of model is straight line, and the exact model might have the slope and intercept as a part of that, right? Whatever the slope and the intercept is. So, but that might not be the most generic model. You might want to use a polynomial, which might fit your data more accurately, right? Or you might want to use a sine function if it's periodic or something. You know what I mean? It's kind of that's just an example of what you do in maths is 1D points, you know, points in 1D. But you can kind of think the same thing with neural networks and things. A particular neural network architecture defines a set of models which you optimize over that set of models with some parameters or whatever. So the big questions in machine learning is, you know, what's a good choice of a model or class of models that you want to optimize over? And how do you know when you're optimizing that you're doing the right thing? Okay, because there's a few things which aren't obvious until you think about them, particularly overfitting and generalization, which we'll talk about right now. So as I mentioned, we could have some data points, and what this code does here, we have some points as X and Y, okay? So imagine there's a set of points we know, X seen, Y seen, okay? And there's some other ones here. I'll talk about them in a minute. So these are just some things. We've gone out and measured some stuff and we want to fit a model to it, Okay, we've got 6 points. One thing we could do is we could just fit a straight line to those 6 points and find the slope and the intercept, and we have a straight line. Another thing we can do is fit a polynomial that goes exactly through each 6 points. So finding such a polynomial is not very difficult. You use something called a Van der Waals matrix, and you do a linear solve on that, and it will give you the coefficients of the polynomial, where the polynomial goes through every point. So the real question is, if you use a polynomial or a straight line, which is going to be better? Or anyone want to answer this question online or in the room? Yeah, okay. It might be hard to guess. So a straight line, for example, is a polynomial. It's an order 1 polynomial, okay? So you would think by expanding your space of models, you can't do worse, right? You should have a strictly better model. Well, there's actually a real sense where that's not true, okay? So take this data down here. We've generated it offline, or maybe just by hand, in such a way that we've created these black points, right? And if we want to fit a red line, the straight line through it, which is a red line, you get that. If you want to use the blue line represents an exact polynomial fit to the black points. So just ignore the red points for a second. So if you look at the accuracy, the precision of the blue line is more or less infinite, right? It exactly fits the observations. But however, imagine you only looked at half the observations, or maybe it's today, this is historical data, and I want to use the model to predict what's happening tomorrow. So I want to make stock market predictions or weather predictions or the house of price predictions, or how many Olympic gold medalists are there going to be in the next Olympics predictions. If I use a model that's too precise, that's going through the data very well, it might not generalize to data in the future. So in this case, we've got some red points here, which are basically drawn from a similar set of the same underlying statistical function, right? Because there's some underlying function that's noisy where you're drawing samples from. And you see the future samples actually fit the red line better than the blue line. Okay, so in this case, we would say the red line generalizes to other data better than the blue line. Yes, up at the back. Yeah. So the question is, that could just be luck. Are we just lucky that the red line is fitting? Yeah. So how do we try and estimate, an infinite variety of situations that could be the future data or so on? So what we generally find, and this is a general observation. So remember, this is an empirical field, but this is applied mathematics, not some pure maths, right? So in the real world, when you get real data, the kind of thing that I'm showing you on this plot, and yes, us lecturers, we've doctored this plot, obviously, but is what you see in reality, okay? So if there's a simple model, if there's some linear model with noise, which the black and red points could have been drawn from, and they were handpicked, but we could have literally done a straight line with noise as inputs and got the same result. Then the polynomial, the high order polynomial, will always be terrible. Okay, it will always overshoot and undershoot and overshoot and undershoot by heaps, and especially on extrapolation, it's going to go wild. But even interpolation, it's going to overshoot and undershoot way, 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 way more than the variance or whatever that you would expect from the underlying model. And so there's this general principle that more complex models, which have more parameters, which will let you fit the data more precisely, they tend to overfit, and they tend to not make models which generalize to unseen data well. So, as I said, this is an applied field, empirical field. The purpose of this machine learning isn't to sort of analyze historical data. Okay. The purpose of doing these kinds of things is to create a program or an application or a tool or something which we can use out there in the real world to do something else. Okay. So when you're training for the letters, the numerals in MNIST, remember the US Postal Service, or whoever it was, they wanted to build a machine that would scan the letters and put them in boxes so that a human didn't have to do it, right? So it's an applied thing. And some machine learning models tend to generalize better to handwriting they haven't seen before than others. Okay, and the general rule of thumb is if you have more degrees of freedom that you're fitting or you're optimizing, you tend to overfit the data that you have. However, of course, sometimes, you can't do MNIST with a linear model. You can't just say there's like one vector in the vector space and we just care about its sort of projection, and that's enough to figure out what a number is. You're going to use some very complicated neural network or random forest or something to try and figure out what the number is. The numeral was, but nonetheless, you still have to be very careful about overfitting. And there's a lot of tricks and things. So first, some models are suited well to this problem. For example, a famous set of neural networks are called convolutional neural networks. And when you use a convolutional neural network, you're kind of encoding translation invariance in the image, okay? Because what it does is, if you know what a convolution is, it's like you take like a pixel and its neighboring pixels, and you kind of, you might apply Gaussian blur or something to an image, if anyone's done any image processing before. But the blur or the filter, they call it, that you apply to that patch is the same to every patch in the image as you translate it around. Okay, it's not a different patch at different parts of the image. In that way, the convolutional neural network kind of sort of understands a little bit, like if the photograph's a little bit, shifted left or twisted slightly or, scaled in or out a little bit, it can deal, you can program it so it sort of deals with that. It doesn't overfit. It's not like you take a cat picture and it says cat, and then you move the cat picture one pixel to the left and suddenly it says dog. Okay, it'll still say cat because most pictures still looks cattish. So you can build that into your model. Like, if there's some process underlying this data you're seeing, and the model should probably be linear, you don't need to use a fancy neural network. You can just do linear regression. Okay, if you have some reason to believe it's linear, and that plus noise. If you have no idea, there's still things like, as in things about the system, like, images are more or less translation invariant. If you move an image, it still is the same thing underneath. It's just moved. But still, if you optimize the hell out of it to a small set of training samples, it will overfit and not generalize well. So how do you deal with this? Okay, so I'm just going to move this little thingy so I can see my own screen. So the best way, or the sort of industry standard way of dealing with this is to split your data into different categories. So there's all the data that you know about, historical data or data you've seen already and you have access to. And then there's data, this is unseen data. So this is what you want your model for. You want to apply your model to new data, unseen data you've never seen before, and make a prediction. Okay. But from your seen data, you want to turn that into multiple sets. Okay. You might use some of it for training and some of it for validation and some of it for testing. Okay. So in this left two is going to be some algorithm that fits the model. Okay. On this right one, it's data that the training hasn't seen, and you evaluate your model against that data and see how accurate it is. Now, this is, if you see how accurate your training set is, if like here, if we just asked what's the accuracy of the black points, you'd get, oh, it's perfect for the blue line. Whereas in fact, it's much more fair to compare the two models on just the red points, because the training algorithm hasn't seen it. It's not sort of correlated, like self-correlated, autocorrelated. And so it's sort of more statistically much more fair. It's a much more unbiased measure to measure the accuracy with this test set. Now, in your model, there might be things other than just the parameters. Like if you have a neural network, which is a bunch of matrices you fill in, fine. You can fill those in and optimize with respect to your training data, but you still might have extra techniques you're using to make it generalize better or to avoid overfitting. Okay. In the case of decision trees, we're going to see how many branches of decision tree, like how deep can the tree be? And this parameter's got a hyperparameter. You know, it describes the class of models, but a particular decision tree is given by a particular set of branchings, which we'll talk about soon. Okay. And what you do is you keep two sets, a validation set and a training set, separate, and you use your validation set to guide the hyperparameter tuning for your training. Okay. There are different ways of thinking about this. Sometimes you keep these completely two different sets. Sometimes you use statistical techniques like k-fold cross-validation, and you know, there's a whole class of statistical techniques for you know, dealing with autocorrelation and things in your data, some of which are, you know, 100 years old, and some of them which are modern, coming out of machine learning, which are relevant. So in this k-folds method, k-fold cross-validation, is you split your training data into k buckets, and you use k minus one of them to train with, and hold one out as validation, and then you validate. And you do that over and over and over again with the different permutations of which is the validation set. And then you try and optimize the accuracy of the validation set with respect to the training. So your optimization problem, when you're trying to fit your model and you're trying to do some optimization problem, you're not directly you know, evaluating the model on some training points. You're evaluating some model on these training points, creating a model and evaluating it on that, and you do it over and over again. Okay. Well, yeah. Well, yeah. I mean, you use this to do the hyperparameter tuning or whatever. Or you use this literally just to validate how good it is. So what you'll find is as you make your model more complex, or you train for longer, or various things like this, what you'll see is the accuracy gets better. So this axis upwards means more loss, more inaccurate. Okay, so down means more accurate. So at some point, you know, as you add more layers to your neural network, as you add more depth to your decision tree, or whatever it is you're doing, you know, it's going to get better and better because you're fitting the data. Because you know, if you just tried to fit a straight line to, you know, an arbitrary function, it's not going to work, right? So eventually you need enough complexity to capture what you know. But eventually you start doing magical thinking. You start jumping at shadows, and you start trying to really fit the exact, you know, ultra fine precision of the training data you have, because you have this huge dimensional space, you know, which is covered by some smooth probability density function, and you only have like 1,000 examples, little delta functions in this high dimensional space that you're trying to fit some functions to. So yeah, eventually it goes up and gets worse, and that's when it's overfitting. And that's what you would see here is, you know, if we change the order of the polynomial to fit the black points, then the accuracy measured on the red points would probably get better and then worse. Okay. Like a zeroth order, well, there's not much slope in this line, but the zeroth order polynomial would be less accurate than a first order polynomial, for example. But like a sixth order polynomial will be less accurate than the first. Okay, so that axis is like the order of the polynomial, or the, you know, how complex your neural network is, or something like that. Or there's other things you do to your neural network to specifically make it not overtrain, things like block out and stuff I'm not going to talk about. Okay, so what we're going to do is we're going to create in this lecture a decision tree based model. I'm going to see how it works. This is more of an expose. You're not going to have to implement your own decision tree. There's a package called decisiontrees.jl. Here. Oh, whatever. I don't know. Oh, I'm on the wrong computer. Oh, no. I don't know what's going on. Why is it doing that? Oh, that's a zoomy thing. There we go. Cool. Yeah. Professional zoomist, I'm sure. Learning. Okay, so what we'll do is we're going to create this tree, and we're going to train it to some data, and we're going to explore some of these ideas of overfitting. So a decision tree, it's a very old technique. In fact, it's a technique used by organizations and businesses and people for eons. For example, if I'm baking a cake, I probably look in my oven and I look, oh, the cake looks yellow, it needs to cook longer, the cake looks brown, it needs to come out, okay? So that's a decision tree, okay? So if I sort of gauge the color of the cake and then have some cutoff for how cooked it looks, and then I might get it out. But it might be like some in between, you know, golden, beautiful color, and I might want to like press it or put a skewer into it or something to figure out whether it's still sticky or not on the inside. And that might be like the second layer of the decision tree that you might make. And so you can imagine any kind of business process or anything that people would follow. There's usually, you know, a set of rules, you know, some heuristics, you know, if this, then I do that, and then I do that. And you see businesses, you know, use flowcharts for processes, which you generally have decisions at the nodes and things like this, you know. You know, at the university, you know, do you pass your course? You know, there might be a set of gates and things for the course. You have to get, you know, more than 50% overall and more than 50% in your exam and blah, blah, blah. Yeah, but so we will formalize a decision tree and program it into Julia, okay? And then we'll see some of the pros and cons of decision trees. The pros are really simple to understand. The cons are it overfits the data really badly and it's kind of not very accurate. And we'll see how to fix that with an ensemble method. So an ensemble means we take, you know, 10,000 models of trees, we call that a forest, and we predict against that. I'll talk about how that works towards the end of the lecture. Basic decision trees. So here we're just going to talk about a data set, okay? So we have two-dimensional features, right? And 3 different classes. So just to look at the data has like an X value, X1 and X2 value. So it's two-dimensional. And there's 3 classes, red, green, and blue. Okay. Now what we've done here is we've generated this using statistics and stuff. Sorry for the formatting. We've got like these multivariate normal distributions. So like a 2D Gaussian probability function, right? So there's one centered at 1, 1, one centered at 4, 2, one centered at 2, 4. These things are the covariance matrices. It probably doesn't matter if you don't know what that is, but basically, you know, they're not just circles, but they're kind of ellipses, right? So in this way, we're creating 50 points drawn from some Gaussian in class 1, 30 points in class 2, and 20 points in class 3, coming from different Gaussians. But, you know, the tails of these Gaussians, or even, you know, quite a large fraction of these Gaussians overlap with each other. So you can sort of see in here, the red and the blue and the green, they're kind of intermingled here in the middle. But on the far bottom left, it's mostly red. At the far top, it's mostly blue. And the far right, it's mostly green, okay? So statistically speaking, if I have this point here, I should be able to say, you know, with high probability, if I find a point in this area, that's probably going to be green. If I find an unseen point here in the middle, you know, it might be, you know, 33% chance green and 40% red and, you know, 28% blue or something, you know, probabilistically speaking. So you're not going to be able to make a prediction which is accurate 100% of the time, but you could still, you know, look at that statistics, give a maximum likelihood estimate or something, choice or something like that. Okay. So if you think of maximum likelihood, there's probably some lines here which divides this into 3 neat regions, and you sort of say, if you see a new point in this region, it's blue, and that region it's red, and that region it's green. So that's our data set. Well, a simple decision tree is just to sort of say that anything left with X1 less than 2 is red, and anything X1 greater than 2 is blue. But here we're going to just give you some code. This code we have been developing, and this all works beautifully I have also in my spare time been trying to create a slightly cleaned up version of this we might look at the end. But what we have here is we have a decision tree is a series of decisions. So you start with one decision, you go left and right. And let's say you go left, then there might be another decision. And then eventually you get to some point down the bottom and it might be a decision. Once you've gone, followed it down to its roots, you should have made a decision. So there should be a good picture of this here on Wikipedia, I hope. Yeah. So like where you can, eventually you get to some leaf node where it gives you one of the categories. Yeah, we don't have a great image of that yet, unfortunately. Okay. So when you consider a node in this decision tree, the node might be an integer representing which class it's from, or it might be some function which tells you whether you're going left or right. Figuratively speaking, right? We don't mean left and right in this image because x1 is left and right. Like it could be branching on x2, or could be some arbitrary nonlinear function of x1 and x2. But generally speaking, yeah. So we could manually create a tree. Okay, the decision function is x1 less than 2. Okay, so that's a true-false predicate function. If it's false, we go left. If it's true, we go right. Okay, so if x1 is less than 2, maybe I should zoom in a bit. It might be a bit easier for everyone, hopefully. Yeah, so if x1 is a bit less than 2, then we say the class is 1, which I believe is red. Yeah, class 1's red. And if it's greater than 2, we say the class is 2. Okay, so that means here the decision is an integer and the children are nothings. I've got another version of this, which is probably a little bit easier to read, that I might cover for you at some point. So as you know, we've been busily creating this course as we go, finding improvements. But you can kind of imagine another way of encoding it is, a decision node, it has a feature, which axis do you want to decide on, what cutoff should be, and what the left and right child should be. So there's many different ways. The only reason I'm showing this is there's different ways of representing the same thing, which sort of have pros and cons. And generally, when you're doing this kind of work, you'll generally just jot down the first thing that comes in your head that works and compiles and everything, and you'll iteratively make your code cleaner. All right, so we can create like a one node tree where the two children are integers or classes. We can define this predict function, okay? So we evaluate the, if the decision is an integer, then you're done, you've already decided. If not, you can execute the decision function on the features, okay? And if you get true, you go right. And if you get, if you get true, you go left. Sorry, if you get true, you get left. Sorry, I said that backwards earlier. And if you get false, you go right. Okay. Brilliant. And what we can do is, if we look at the accuracy of this model, is if we predict. So we have all these x's. So we probably should spend a bit more time on here. Capital X is all the input data. Capital Y, a little y is and it's a matrix. Okay, so there's n data points with k dimensions. No, sorry, d dimensions. So this would be like a 2 by n matrix. And y is the classes themselves. So 1, 2, or 3. It's a vector of 1, 2, and 3. So for each of those x's, we make a prediction, right? And for every one of them, we see if they're equal to yi. Okay, so for each I, right? So for each I in the size, size x1, so that's the number of points, we make a prediction and we ask whether it's equal to that, okay? Now, in Julia, a Boolean number is a bit like a 0 or 1. False is 0, 1 is true. So if you take the mean of a vector of Booleans, or in this case, it's a generator of Booleans, but it doesn't really matter, then you're going to get a number between 0 and 1, inclusive. Okay. If they're all true, you'll get 1. If they're all false, you get 0. If they're half true, you get 0.5. So this encodes the accuracy of the model. For how many of the points in X did we get the correct answer? Okay. So this is throwing away all this logic about validation sets and test trainings, test sets and stuff. This is just training on the training set and ignoring everything else for the moment. Okay. So it's a bit sort of self-referential. So we're going to find the accuracy and we're going to plot all the points. And so for this model where we've split the region up like shown, it's accurate 62% of the time. So 38% of the time it gives the wrong classification. For example, these blue and green points here are wrong, but 62% it's right. There's a lot of blue on the right, and there's a lot of red on the left. Okay. So, you know, as a first order thing, you know, just picking some integer out of the air, it's not so bad. It's over, there's 3 classes and we're well over 50% accurate. So that's fine, but we can do better. Okay. So we can add more nodes. Like for example, we can take the right child node here and we can change it to be a cutoff on X2. So that's the Y-axis on the plot. So that if X2 is greater than 4, we get to class 2. I keep reading this wrong, right? If X2 is greater than 4, then we get the left child, which is class 3. And if X2 is not greater than 4, we get the right child, which is class 2 or green. And now with this extra decision, we've gone from being 62% accurate to 71% accurate. Okay. So you can imagine as we add more and more fine grainedness to this model, we might be able to get this accuracy up higher and higher. Okay. So we got this little show function. It's sort of saying it's a tree. In this cleaned up version of the code, you can actually kind of, which I will post online and let you know about. You can kind of actually see what the which feature and what the cutoff is. This very, very weird thing here, I don't really want to explain it. This is some kind of symbol that the compiler generates whenever you create a closure. Okay, so a closure is like an anonymous function, right? So it's anonymous to us, but the compiler has to call it something. And in Julia, everything's named with a symbol, which is like a string, which the compiler knows about. This var thing is a string macro, which lets you use variable names, which you can't normally use. These ones have hashes in them, which is the comment symbol in Julia. So you can't really have a hash inside a variable normally, but that's what that is. So not particularly important, but you can kind of see that, you know, after the first decision, you might get a 1. After the second, unless you're going right, in which case you might get a 3 or a 2. And you can kind of add more and more children. So now we're going to split up the left half so that part of it's blue and do that. Now, here Yoni hasn't chosen a very good cutoff. We can kind of see we've made the model more complicated, but we've actually made the accuracy go down. Okay. So we probably need something to optimize where to put this cutoff to make it more accurate. So that's what we're going to do in a moment. Okay. Okay. So as we can add more and more to the tree, accuracy can increase. Okay. And you know, in principle, if we're really careful about dividing this space up into rectangles, we could essentially, like the polynomial, we could essentially have one rectangle per point and make sure that each rectangle has its own region, which is correct. But this is going to be overfitting because, like I said, in this middle region, you know, we could draw more and more samples from the unseen set, you know, in the future or whatever, and they're just going to come out more or less random in there, right? Because it's sort of a mixture of the three different classes at that point. So, yeah. And also, you're going to do weird things like this red point here might make this region red, even though it's more likely to be green. Okay, so that's what could happen here with overfitting, and we'll see that soon. So now we need to do a little bit more software engineering just to show you how you might capture all the data and optimize it over the data to create a tree. Okay, so what we've done is we've taken the exact thing as before with the children and the decision, and we've added the data into it. So we've created another struct. So it's, we're sort of iterating on our code, making it a bit more complicated. We've got this very beautiful name, decision tree node with data, and it has a lot of stuff in it. So what these X's and Y's are, these are the X's and Y's of the subset of data, which is within this subset of the tree. Okay, so whenever you consider a node, zoom. Okay. Whenever you're in a node, you're in a rectangle. Okay, so the X and Y for this node would just be for the points that were within that rectangle and not the ones outside. Okay, going slightly too far. Sorry. So that's the data inside the node, and then we're going to recursively split. We're going to say, okay, can we split this data? And then we have to know, like, along which dimension should we split, what value should we split at, and we're going to create an algorithm that will do that for us automatically, an automatic splitting tree. Okay, so we start with a simple decision tree with all the data, just defaulting to the entire sort of plane being in class 1. Okay, so we create our auto split tree, and then we're going to create an algorithm that's going to mutate the tree and make it more and more accurate for us, sort of iteratively. So the way we need to sort of optimize this is to make it more and more accurate. So we can have a look at the impurity, or the loss function as being the impurity, which is like the number of things which are mismatched. So what we're going to look at is a balance of two facts. We've got a left set and a right set, depending on where the split is. And we're going to look at the average accuracy on the left plus, or the average inaccuracy, the average mismatch on the left, plus the average mismatch on the right. And we want to minimize that. Okay, so if we're split into a world where all the red's here and all the blue's here, and we divide it in the middle, right, then there's 0 inaccurate on the left, 0 inaccurate on the right. If you're in a world where, if you decide to split in the middle of the blue, you might have everything to the left of that split is accurate, but on the right it's not. Okay, so by summing up these two things, we're going to find the sweet spot where we're most accurate on both sides. So that's what and that's our loss function. Okay, so this is the thing we optimize. So what we got here is fine splitting rule, and it's not a particularly complex thing. I'll go through the loops in a moment, but it's basically brute forcing it. What we're doing is we get all our data, X and Y, from the node, and we start with, tau here is the place that we split, and feature here is the feature that we split at. Okay, and what we do is for every feature, we're going to test every possible splitting point. Okay, so n here is the points. So for all n points, for every dimension, we're going to come up with a candidate splitting position. Okay, so if we're looking at the jth dimension and the ith point, xij is going to be everything equal to and less than that, we're going to say is left, and everything greater than it's right. Okay, so that's what this next line of code is doing. So given that this xij is our splitting point, and j is our dimension or feature to split on, we divide the world into two halves. And then given that, what we do is, well, first, if we haven't really divided the world at all, because we're the extreme left or right, we just ignore everything. Why on earth did this come up? looking at multiple screens, isn't it? Then given that we've split the world into two halves, we take the mode on the left and the mode on the right. Okay, so this is a heuristic. All these algorithms, neural networks and everything, you'll find they're very heuristic. So if there's most red on the left, then we color it red. And if it's most green on the right, then we color it green. Okay, so that's the mode. What's the most common class on the left and the right? And then we calculate this loss function, which is exactly this thing here. These are just means of mismatch. Okay, so that's means of misprediction. That's what this is. So for each one of those, is the prediction correct or not? And we're just looping through. We've started with a loss of infinity. Remember, more is bad. So if the new loss is less than the existing loss, then we replace our candidate set of things we're going to return with, the feature being J, and what should the cutoff be? What is the loss? We just preserve that so we can kind of use it. And that's also iterating over the features. So for each dimension, for every possible cutoff, we're finding the best one by brute force and returning that. Okay, we're returning it as a rule, left value and a right value. Okay, so again, it's another thing where we might iterate over our code and try and make this a bit prettier in the future. And that might be a process we look at the end of the lecture if we have a bit of time. And here we have to repeat ourselves and define how we do the predictions, but it's exactly the same code as before. So like we evaluate the decision rule, and if the result's an integer, we return that. If it's another thing, we go to the children. Okay, so how do we build a tree? Well, you have this hyperparameter, which is your maximum depth. Okay, how deep do you want the tree? That's this parameter here. And what we do is we start with some initial tree and we refine it. Okay, so we start with a simple plane with basically no interesting features in it. And we add a left and a right child to that, and then we descend and we add a left and right child to each of those. And we keep doing that until we've gone too many layers. Okay, so this sort of happens sort of recursively. So we're creating these we're asking for what's the best splitting rule, and then we're creating a left subset of the data and a right subset of the data. So here we're picking only some of the x's that are on the left and some of the x's that are on the right, and we're choosing the left value and the right value. So that's the class. And then we're looking at the, that's, shouldn't there be a function in here somewhere? Maybe that's what that is. Oh, no. Oh, no, the function might just be, yeah, no, that's a value. Sorry. Yes, in this representation, that's just a value. Apologies. So now we recursively, once we've created these new nodes, we refine them, and then we refine them again, refine them again. So this will go on forever unless one of these three things happen. One, you're left with 1 point, so you're like golden. I don't need to split again. Or you might have more than 1 point, but they're actually on top of each other, so you can't split them. That's what that one is. Or you've gone beyond your max depth, which means your tree's too big, too complicated, and we just want to stop now, or we're going to run out of RAM or overfit or something. So if we do this, remember this max depth goes to infinity, so we're going to split down to these regions where they're either perfect or there's exactly 1 point in them. And we see this picture, okay? Yuck. Doesn't that look kind of disgusting? Okay. So what's wrong with this? So what we've got here, we've got these little wafer thin slices of data in the kind of regions, and they got put in there so that we could fit every single training example perfectly. No training example is wrong. Remember, this is a statistical model, it really is a mixture in the middle. You would expect to be sort of less certain and to get some of the stuff in the middle wrong. That would actually be okay. Okay. So we'll talk about this again in a second, but let's just have a look at our, sorry about that. Look at our tree here. So we can count, for example, the number of nodes in our tree, because it's not necessarily a perfectly balanced tree. It might terminate in some edges before others. It might be and we can count the depth of the tree. So it's had to get only 139 nodes, but the depth has gone as much as 70. So it's like 70 yes/no questions, 20 questions. Who's played the game 20 questions? So that's actually an awful large number of questions. To sort of see how it's building it, we've got this algorithm here, and we're looking at this tree at different depths. Okay, so between depths 2 and 100, and we're going to plot. We're going to make a video of this in a moment, but first, let's see what it does. The summary includes the accuracy. Okay, so a number between 0 and 1, how many points did we get right? So as the depth goes up, first note the accuracy is getting bigger and eventually gets to 1. Okay. The max depth actually gets saturated at some point. So at 70, it doesn't need to split anymore. So you're allowing 71 splits, but it only needs 70. And then num is the number of nodes. Okay, so the number of nodes or number of rectangles is going up until we get to 139 rectangles, and every point's accounted for. But if we were to plot how accurate this is versus the depth, well, hang on, this is actually a better one. So here's a picture of, or a movie, an animation of what it's doing. So we'll reset. So we start with 2 regions, 3, 4. We add more and more regions to this plot as we're allowing the depth to get higher. So the model's becoming more and more refined. It's fitting more of the training data. But that doesn't necessarily mean it generalizes to unseen data better. Okay. So what do I mean by that? So let's take some data. So we make 100 in each thing, in each class, and we take some other data. Remember this make data function just evaluated the Gaussians, put the points in places. And we take some validation data. So we're going to train the tree on these 100 points or 300 points, and we're going to evaluate it against these 120 points. And we're going to see how well it does at different depths. Okay, so for each depth from 2 to 150, we've got more training points. We need a bigger depth. It's going to do something interesting. So first off, the validation accuracy is below the training accuracy. So this is normal. You've always going to have some degree that the thing you're optimizing is better, is more accurate than the stuff you haven't seen that you're not optimizing over. Okay, but more interestingly, what we get here is as the blue goes up and up and up and up, the validation results aren't getting any better. They're sort of wobbling around. And what you'll see in most models, like if we do a random forest or something, which actually has higher accuracy, it's going to be more up here, it will actually tend down again. So there's going to be some sweet spot where maybe depth of 20 or 50 or something is going to be the spot you want, because that's the spot that will give you the best accuracy for unseen data. So remember, the purpose of this whole exercise is to find a model that generalizes and works for unseen data. It's 5:55. We're going to take a 10-minute break, and we'll get back into our last segment of the lecture at 6:05. Thank you. But you should, reality, you should just use whatever. Because the bottleneck's not usually. Okay. Okay, it's 6:05. Welcome back, everybody. What we're going to do for the remainder of the lecture is just talk up, wrap up our discussion on decision trees and move on to random forests and ensemble methods. Then hopefully we'll have a little bit of spare time for a bit of discussion of project 3 and some of the other sort of aspects like that. So what we saw in this little experiment was that as you make your model more complicated, your tree more deep, you get to fit the training data more and more and more until eventually you might even get 100% accuracy. But in reality, the answer on the validation set, in unseen data, might not be very good. So in this case, it's actually not getting much above half. So this isn't a very powerful, accurate model. We've only got 3 classes here. We can't do better than 50% accuracy or something like that. Now there is some, we could actually measure we could create the optimal surface here and actually measure the maximum accuracy of this model, because we know that the underlying model, the underlying statistical distribution, but yeah, unfortunately we don't have that on this plot. All right, so trees. At the end of the day, trees can be used, and any of these machine learning models can be used for more than just these classification type of issues. At the leaf of your tree, instead of having an integer representing the class, you could have some number, some floating point number, for example. So if you want to look at the price of a house, for example, where you could say, you could branch and branch and branch based on number of bedrooms and bathrooms and distance to city, and your leaves could be, how many thousands of dollars is that house worth? Okay, so it's like some kind of flowchart sort of thing. You throw through and then you go down. Okay, this house is worth, $650,000 or whatever. Right. So you could use it for regression. So not just anything that's just continuous. You could regress, for example, even a higher dimensional vector. So for example, instead of having the number 1, 2, or 3, we could try and regress the probability that the point is in 1, the probability the point is 2, and that the probability is in class 3. And then the regression problem we're trying to do is actually fit the actual probability density function for the 3 classes, okay, as a function of all the x's, capital X's. So yeah. And generally, if you have a categorical feature, so not only the outputs might be something weird, the inputs could be something weird like a string, okay? But when it's a string, in the housing example, the string might be, standalone house, apartment, townhouse, and there might only be 3 different possible strings, right? So what you could do is do something called one-hot encoding. So you come up with 3 new features, and the first one might represent townhouse, and if it's a townhouse, that features 1. If it's not a townhouse, that features 0. And the second one for apartment, the third one for detached house. And only one of those 3 things will be 1, and the other 2 will be 0. But the advantage of this is we've now embedded it into this space, this vector space, so it's going to fit in one of these X matrices of floating point numbers, okay? So we've taken what was originally strings, and then now we've put it into a matrix. So this is generally useful because you want to put together your code as Lego bricks, right? You don't want to write a decision tree. You want to use some package from the internet that someone else has done all the hard work from you, and you want to, take your data frame or whatever, munge the data, put it into matrix, and then send that matrix to someone else's code to train some model for you and worry about all the cross-validation and all these things, and then give you a model back that's, you know, in somehow ideal. You know, they've dealt with all the optimization problems and all the stiffness and overgeneralization, overfitting, and this kind of thing. So, for example, packages which are pretty famous, there's decisiontree.jl, which is a pure Julia implementation of decision trees. And there's another one, xgboost.jl. This is a sort of commercial grade C library. So in that package, you send it a pointer to a matrix and a pointer of features and a pointer to a vector of you know, the classes or whatever, what it is, probabilities, you know, whatever you're trying to regress. And it will return back, you know, some model that it can evaluate for you and stuff. And it's very fast. So it's written to be like multi-threaded and use your CPU well. And it's also quite accurate. Okay, so XGBoost is using something called extreme gradient boosting. Okay, so it's very much related to the random forest we're going to see soon, but does it a bit differently. Probably better in a way, but we need to see something probably simpler a bit first. And, you know, you might want to, you might get some data and you don't know how to express how to model it well, because it's the first time you've seen this data. So what you'd probably like to do is to use some interface where you can switch up the models. I want to use a neural network. I want to use a tree. I want to use a SVG or whatever it is. There are well-known interfaces for this. In Python, there's scikit-learn. Julia's MLJ. There's scikit-learn.jl, which just is a copy of the Python package scikit-learn. And this is where I was getting back to what I was saying before. The interface these packages like is, you know, something like, oh, give me a vector of a matrix of features and a vector of answers, and I will do the rest for you. And you just specify the kind of model you want me to fit. Okay, and I'll go away and fit it for you. And then you could get it to try 10 different flavors of neural networks or whatever, and it will give you 10 different answers. You can see which one is most suitable for you. Okay, so in practice, some of the things which you care about, for example, is how long does it take to train? How long does it take to evaluate? Because, you know, in business, time is money, right? You can't have a Google search or something relying on a neural network that takes 10 seconds to evaluate, because Google wants to give you the answer in 100 milliseconds. Right, so there's, you know, a lot of trade-offs here that you might, a lot of reasons you might want to try different models. One being like the accuracy, and second one being the generalization, like whether it's overfitting. And the third is, you know, all these externalities about how much it costs to run and how much hard disk space and RAM it uses and so on. Okay, so let's go back to MNIST. MNIST, for some reason, let's get rid of this. Yeah, beautiful. MNIST is this data set with the numerals, remember? So these things, that's MNIST. So if, let's say we want to use one of our decision trees on that data set directly. So on last week, we did look at using a linear model on that data set, and we ended up getting, I can't remember, was it 83% accuracy or something? Let's say so here. I believe we should look this up just before. %86 accuracy with our linear model in that high dimensional vector space. So let's try the same thing, but now with a decision tree. Might be arbitrarily deep. We've got 60,000 test images and 10,000 validation. Oh, sorry, 60,000 training images and 10,000 test or validation images. And we're going to, well, first off, we're just going to use decision trees.jl. Okay, and then we're going to use make a random forest. So decision tree.jl, you know, it's been written, put on the internet, and so on. It has its own interface, its own API, so you can go and look at the documentation. This is the package here, and you can kind of see you can access this package through MLJ and scikit-learn. Okay, so these things sort of aggregate, you know, dozens and dozens of different machine learning models, and you can use the one MLJ interface or scikit-learn interface to access those models. This is a little bit about how it works and how you can install it, and you can probably click here, and it should come up with some documentation about how to use the API and stuff. So in this thing, it has this basic function build tree, and you give it the training, the Y train, and you know, the training data here, for example. It doesn't need a validation set. And then it has some hyperparameters, like how many sub features and blah, 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 blah. Okay. So how many min samples leave? So this is where we wouldn't split where there's one, but maybe you don't want to split if there's 5 or something. And this kind of thing. So what it does is on the MNIST data, it returns some model which has depth 22 and 3,327 different nodes. Okay. So if you want to think about these are like not hypercubes, hyper rectangles in some really high dimensional space where there's a dimension for every pixel in the picture. Okay. So it's a bit of a weird model, but it kind of works. And you can see here we get 88.6% accuracy. So it's 2.5% more accurate than our linear model from before. Eventually, as you get into more complex models, we'll get up to 90%. Maybe really good neural networks will get closer to 99% or something on this data set. So yeah. So that's it using, you know, not some code that's really, it's not much more complicated than the kind of thing that we've done in this lecture. So just let me show you the code, go off on a tangent. So here's a decision tree classifier, and it has similar things as we have, but I just want to show you the split function. This is probably a little bit more complicated than I would have liked, unfortunately. But it's doing a similar thing in terms of splitting, but it's using sorting and stuff to make it faster. And the thing I can't seem to find is the loss function it's using. Yeah. So what it uses is an entropy function to determine the splitting point. So you know, it uses a slightly different loss function, which tends to work well for tree. So it's like basically what is the decision which maximizes your sort of Shannon information about the data set. Yeah. All right, cool. Yeah, so what we're going to do is we're going to use their tree-based implementation and show you how to turn a single tree into a forest of trees. So what we mean by a forest is, you know, we have many, many tree models. And let's say it's a classifier. So, you know, it says it's blue, and then some other tree says it's blue, and some other tree says it's green, and some other tree says it's red. So you have like 10,000 different trees. You evaluate, get a prediction from all of them, and then find the most likely outcome, or the most common, the mode of those predictions. Okay, and through this method, you don't you can actually improve your accuracy. And the way that I like to think about that is that instead of having these sharp boxes everywhere, what you have is you have a superposition of 10,000 different trees like this one, but trained on slightly different data, or, you know, different choices made. And what you end up, instead of sharp rectangles, you end up with this fuzzy sort of landscape. So you know, I think in all the trees, the far right's going to be green and the bottom left's going to be red and the top left's going to be blue. But in many of the trees, they'll disagree about points in the middle. And therefore, they'll, you know, they're not going to be overfitting in the middle. I mean, it's not going to be 100% accurate because 100% accurate is not possible, but it'll still be a lot better. Right, I'm just scrolling down too fast. So formally speaking, if what we would do is we would take the predictions from, like if it's a regression problem, for example, take the prediction from each tree and take the mean of that, okay? Or in terms of probabilities, you can think if you've predicted blue, that's sort of like your output is 100% probability blue, 0% probability green, 0% probability red. And you can take an average of those vectors, okay? All right. And what we do to make it work is we train a tree on a subset of data 10,000 times, for example, or 100 times, okay? So we take, let's say we had 60,000 things in our training set. We may take, you know, 10,000 of them at random, okay? And when we say with replacement, it's possible that we choose the same input point twice, okay? It's not like exclusive. Okay, and then, so, yeah. So the data used to train each one is a little bit different, which means the model that comes out of each one is a little bit different, okay? And if you wanted to try and fit this, you know, when we allow the tree depth to grow and grow and grow and grow, eventually it's fitting every point exactly. If you imagine now, in a lot of these trees, a given point might be missing, okay? Which means even with infinite depth trees, you're not going to have knowledge of that point. So you might get that point wrong. So the model that comes out from averaging all these different trees together has some uncertainty. And in the areas where it's a bit confusing and you know, human can't eyeball what that should be, the model will kind of, you know, say, okay, 30% of the trees said red and 40% said green and 30% said blue. And you know, it's kind of a bit mixed up, which is good because it means it's not overfitting. Okay, it's not like really, really certain about something which is actually quite marginal. Okay, so yeah. The other thing that you do with the random trees is because you have so many different models, you don't need a big depth to get good results because different trees could look at different dimensions and split them up for you. The other thing is you don't need to use all the features in every tree. So what can happen is you can have less powerful models, but averaging over many of them and your accuracy increases. And this was really the insight. There's a famous paper that led to XGBoost, which was talking about gradient boosting. So basically the idea is that you can combine or add together a bunch of weak learners to create a strong learner, okay? So if you have, say, some learner which is so accurate, and so long as you can add a new learner which is somewhat orthogonal to it, to the ensemble, you can always get it a bit more accurate, a bit more towards optimal, so long as it has some information or some discrimination that the current stuff doesn't have. So yeah, so there's a sort of mathematical sense in terms of information theory where you could quantify how accurate these things are, and you can sort of see that this sort of averaging thing increases the, you know, the information criteria, whatever. So okay. So typically in this random forest, you know, you'd use something like square root of D as the number of features. So sometimes in some models, you might have 100 features or some large number of features. The kind of stuff we're dealing with, it might be 10 or 20, like in the tutorial in project 3, is what you'll find is it's sort of that order of number. Okay, so we have we're picking an n random points and square root of, you know, some random number of columns, and creating a submatrix out of our full input matrix. We're creating some submatrix and then training a model on that and storing that model. And then we're going to do another sampling of that matrix and do it again and again and again. Okay. So here's the heart of the algorithm. All right. So you can find, this is the one from decision trees. All right. And what it's doing in here. And you'll find this here. There's a build forest. So before we called build tree to build a single tree, this is build forest. Again, we got the output labels and the input features. So that's a vector and a matrix. And some hyperparameters like the maximum depth and things. You know, we want, you know, maybe just 10 trees, or maybe 100 trees, or 10,000 trees. It might vary what you do. So essentially, well, first we have this loss function, which is computed in terms of entropy. So it's an information criteria. Think Shannon entropy, if anyone's familiar with that. We were trying to, what this means is we're trying to take the cut, which maximizes the information that cut gives us. Okay. And then every time we, this is two different ways of training it, depending on whether you want it to sort of train randomly, because there's some randomness in this, in the subsamplings you take, or you want to make it repeatable. So you can put the seed into it, okay? There's this threads thing. You don't have to worry about this. What it does is it puts the different loops, the for loops, on a different thread to make the algorithm faster, okay? And so for each 1 to n trees, we're sampling n samples of 1 to t with some random number generator. And that's fine. And from there, we're going to like build a tree, okay? And we're going to stash that tree in some vector of trees, which is called the forest. So forest is a vector of trees, n trees, okay? So we're training them all with different sets of data. And then there's the apply forest, which is like our predict function, which basically goes through all the trees and applies a vote for each tree, and then finds the majority vote, essentially. I think this bit's a bit fancy because it's doing regression and classification at the same time. So that's basically it, right? It's not so complicated. I don't believe in here we have a beautiful graph, unfortunately. But you'll be, oh dear, why did that happen? How did that happen? Sorry about that. Great. Okay. Just check the chat. All right. So yeah. Are there any questions that anyone wants to ask me about random forests before we have a discussion of project 3? Anyone online? All right. You know, I find this to be a really kind of fascinating sort of topic. So it's kind of be interesting to see. There's like 30-year courses on neural networks and machine learning that you can do if this is something you find interesting. Okay, let's have a look at project 3. So this is going to cover both this sort of analysis of data sets that we did a few lectures ago and the random forest we're talking about today. Okay, so it's not due to the 20th of November. And you know, the general kind of thing we do is sort of like the last two. I believe it's a single person assignment rather than a group work. You'll get marked for the, basically being able to use GitHub and submit it. The analysis of the perspective seminar tomorrow, so I encourage you all to come along or to watch live. I'm sure it'll be great. And 80 points for what we'll talk through here, okay? So I'll skip through that because you've seen it before and you can always ask in the tutorial. So the main task is to deal with house prices in Melbourne. There's this thing called Kaggle. I'm not sure if you guys have seen it before. Monty-Python. Why does it say Monty-Python? Should I be worried? So Kaggle is a platform for data scientists to sort of work together in an interesting way. So there was this thing called the Netflix Prize many years ago, where Netflix decided they wanted a better recommendation engine. And they put up $1 million for the person to come up with some machine learning model that could predict what movie someone might like based on the movies they've already watched, okay? So Netflix doesn't, ask you tons and tons of questions. It just observes you've watched this show and that movie, and then it's like, oh, you might like that movie. And kind of the more accurate that is, the more addictive it is. The more you watch it, the more likely you are to watch it more and pay them more, keep paying them, and not sort of leave. So there's a lot of money on the line for a platform like Netflix. So they basically spent $1 million and put some data up on the internet. And to win the prize, what you had to do is create a machine learning model. You give them the model and they could evaluate it against some test data, which you haven't seen. So they give you training data, which you split into validation and training to do your own modeling and stuff. And then they have a secret holdout set, which you don't know about. And once you've submit your answer, they can test it on that. The person who gets the best result wins. But, they didn't really want the winner. They just wanted, a bunch of ideas and also to drum up some publicity and things like that. But Kaggle is a platform where anyone can do this. So it's a platform for putting these kind of problems where you put in the training sets for the people to use and the holdout set, and it'll kind of like, it'll deal with the process of teams joining and making submissions and letting them look at your data. And you can submit just some free project out of interest, or you could put like $50,000 on the line for the winner. So yeah, so there was this data set we grabbed from Kaggle for the Melbourne real estate data, which we've got here. I think we also got the Olympic data from Kaggle. Okay, so that's what it is here. So you can follow that link and kind of see what this was about and what they were trying to do. But there's like different tasks they send you and things like that. So, but what we want to do is we want to just do some basic things with this data, right? It's a CSV file full of columns, like I mentioned, like the distance of a house to the CBD of Melbourne, the postcode, lots and lots of different things. So, at the start of the project, you're going to kind of have to put it in a data frame or whatever, and or not even a data frame, but just start extracting columns, examining what's happening in each column with histograms and things, compare different variables, see if you can identify some trends in some graphs, see if data's changing over time. And so this is really exploratory kind of stuff. We've got task 4 and 5, where you're actually going to start dealing with geography a little bit. So in task 4, this data is always sparse. There's always missing values. So in task 4, you're going to try and figure out what's the postcode, because it might be missing, but you might know the suburb name or something. So you're going to have to come up with your own algorithm, which maps from, say, suburb name to postcode. And in a way, this is a kind of like a machine learning problem, right? You're going to create your own algorithm for going from a set of features, which might be like council area, region name, or whatever, and you're going to predict postcode. Okay. So you're meant to take away something a little bit meta about this. Often in machine learning, if you're trying to do something practical, it might be best to start with some obvious handwritten algorithm that just, puts data into buckets or dictionaries or whatever. And then if that's not good enough, you can go away and do machine learning. Because what you see over and over again is someone tries to apply some fancy machine learning and spends months on it. And then someone goes along after the fact and implements some naive thing with a dictionary and it works just as well. Okay. And this can happen and someone's wasted the time without really knowing what's important. So often it's very important to kind of do this handwritten thing first and then move to more and more complicated things like machine learning as you need them. So once you kind of have some, more accurate data about the geography, you're going to start plotting it in a map. This is kind of fun. It'll be interesting to see what you guys come up with, and you can sort of use your sense of design and creativity here. Which is kind of fun. And then finally, the last two bits are dealing with random forests. We're going to apply the random forest from the package to make a model predicting the price of a house. And you're going to have to create a training set and a test set and compare them and figure out how well you're doing, okay? But yeah, you'll have some model which will let you buy a house in Melbourne if you're so inclined. And finally, what we're going to do is you're going to go through and take this code at the end of the lecture that I got here and make something like it of your own and make it like a package or a module or whatever, which will help you build and use build it like train or build random forests and evaluate the random forest, given that you already have a package to deal with the decision trees themselves. Okay, so we could make you implement both, but we feel it'd be time consuming. I don't think it's difficult. If you want to implement a decision tree, you may go ahead, but just use decisiontrees.jl as your decision tree and go ahead and do that. I kind of feel like we've reached the end of the content and it's been a long semester for everybody. And it's 6:37 at night on a Monday and I kind of feel like everyone can get an early break. How do you all feel about that? Yay. Okay. So before we do that, if anyone has any questions, please let me know. Guys at home, I'll give you a moment. Otherwise, I do strongly encourage you all to participate tomorrow, whether here or at home. Nathan will undoubtedly give an excellent talk. I've found the previous two seminars very interesting myself. And yeah, hopefully you'll see Yoni, me, and a couple of Pauls potentially even tomorrow. So thank you.